discussing today, are two related sites. I'll go through an introduction, so if we can, and some common site descriptions. Then I'll go through the application of bioremediation along with the results and conclusions at the first site, and then Glenn will take over for site 2. So now if we can go to our third slide, I'll go through some background to put us on some common ground. So for these particular sites, what we're going to be discussing is the reductive dechlorination degradation pathway. So just for some brief overview, I have outlined the pathway below, and I've only used abbreviations for the chemical names and haven't put down the formulas. So in general, one would be starting with the most chlorinated product, PCE or perchloroethene, which has 4 chlorines. And then there's a sequential removal of chlorines. The next product, which happens to be the constituent of concern at our 2 sites, is TCE or trichloroethene. I've then depicted the most common isomer of dichloroethene, cis-1,2-dichloroethene. Now you'll see in our subsequent slides that we just used the abbreviation DCE because what we've done is sum all the DCE isomers detected. Another chlorine is removed, and we have the final chlorinated product, which is vinyl chloride, or VC. Then the ultimate end goal of reductive dechlorination is the innocuous end product, ethene, and then also ethane. You'll also see in our presentation that we have summed ethene and ethane. Now, here when we're discussing bioremediation, what we mean is that we have done both biostimulation, which is the addition of substrate, because in reductive dechlorination, the chlorinated solvent serves as the electron acceptor, and frequently what is needed to further progress the reaction is additional electron donor. And what we've also done at this site is bioaugmentation, or the addition of microorganisms, in this case specific degraders for trichloroethene. And we also have at this site, but won't be discussing trichloroethane. So we have degraders specific for that as well. So if we can go to the next slide, slide 4, and I'll describe, give you a big overview of what you'll be seeing in this presentation. What we're looking at is sort of the difference that we see in performance at 2 very related sites. These sites are only about 7 miles apart, and they have very similar hydrogeology. And so if you look at, Dora, can you advance to slide 4? Thank you. Okay, so what I'd like to discuss are the big differences that you'll see in site 1 and site 2. So just to set the stage, the left-hand side of both figures are the molar concentrations of chloroethene. And what I'd like to point out in site 1 on the left-hand side, this solid dark line is our total chloroethene moles. And you can see that those are decreasing during the course of our bioremediation program. And this mustard yellow line with the dots are the combined ethene and ethane. And you can see that we have converted almost all our chloroethene moles at site 1 to ethene and ethane. And this is just an example result. Then at site 2, on your right-hand side, you can see after our amendments, we do see some decrease in TCE concentration. TCE is the line that is dark blue with diamonds. And we do see appearance of daughter products. You can see cis-DCE and you can see vinyl chloride. However, we don't have the total reduction in chloroethene moles as we see at site 1. So now if we can advance to slide 4, some other common elements at these 2 sites. So are the hydrogeologic setting. At both sites, there's a very low permeability overburden of clay and silt with some isolated sand lenses. And beneath this is a bedrock of dolomite with high permeability fractures. And in the photograph at the bottom of your slide, you can see a core that was collected at site 2, and you can see some of the fracture locations along with the depth indicators. So now we can go to slide 6, which is, if we'll go to the next slide, Dora. I guess it's just taking a while to come up on my screen. I don't know how it's
doing the advance. Sorry.
Yeah, I don't know what you all are seeing out there, but at any rate, okay. So now we're at an illustration of a bedrock well construction, which is the same for both sites. There's solid casing through the overburden and 2 feet into the bedrock, and it's open core below. And then when there were amendments made, the transmissive zone was isolated with a packer. So now we'll be going to the next slide, slide 7, and we'll get into the specifics of Site 1. So I'm waiting for the next slide to come up because there's, I guess, not really a lot to say about the bedrock well schematic. So here we go. Okay, yes, yay. We have a plan view of Site 1. What I'd like to especially point out here are some monitor well locations and some of our application areas. So in the sort of upper right, you see the overburden test area, and then monitor well 7A, which is an overburden well. I'll be presenting results from it. Down gradient from the overburden test area is the bedrock test area, and a representative bedrock monitoring well in that area, 17B. And then down gradient is another bedrock monitoring well, monitor well 11B. And groundwater is generally flowing south-southwest across this site, with north being at the top of your screen. So if we go to the next slide, which will be slide 8, I have a cross-sectional conceptual model that you can see of Site 1. And in this cross-section, the overburden pilot test area is at the rightmost part of your screen. The bedrock area is then down gradient. You can see the groundwater flow arrows moving across the top. And then that down gradient bedrock monitor well 11B that I illustrated, that I pointed out on the previous slide. You can also see the elevation of the water table and depictions of the overburden with a sand lens and then the dolomite bedrock. If we go to slide 9, the next slide, I will start giving you some background information on this setting, both chemically, of Site 1. At Site 1, our chlorinated solvent concentrations range from fairly low ppb numbers to about 6,000 part per billion or micrograms per liter. There were several indicators of natural biodegradation at this site. For example, the daughter products of TCE reductive dechlorination were detected, primarily dichloroethene in the overburden source area. However, dichloroethene and vinyl chloride were also detected down in the bedrock wells. We did detect methane and ethene prior to any kind of bioremediation activity at the site. In addition, the site already had a negative redox potential indicating anaerobic conditions. Our microbial testing before we began the bioremediation program indicated that we already did have the presence of suitable microorganisms. We had Dihalococoides and Dihalobacter, although the levels were on the low side and not optimal for bioremediation. We also tested for several degrading enzymes. Only one here is mentioned, vinyl chloride reductase, although we did look for TCE reductase and BBC1. And we all had low-level detections of those enzymes as well. The site had a neutral pH, which is very favorable for Dihalococoides. Our sulfate concentrations in background ranged from about 170 to a little over 300 milligrams per liter. There was no sulfide detected at our site. Now, one of the main indicators for the need for bioremediation at this site, in addition to the fact that we did have some of the daughter products and not all ethene and ethane at this site, was that our total organic carbon concentration was less than 10 milligrams per liter. So we knew we needed to amend. So if we go to the next slide, I'll cover the timeline of our bioremediation program. So in preparing this presentation, we realized how much microbial data we had, and but in the interest of our presentation, confined it to mainly showing the D. helicocoides results, at least for site 1. So at this particular site, first we applied our substrate in the overburdened source area. Now we used SRS, which is a product of Terra Systems. SRS is an emulsified vegetable oil. It also has lactate as a fast-acting carbon source, and it includes B12 along with other nutrients. When we applied SRS in a bedrock application, it was custom prepared with a larger droplet size for us. We monitored our site conditions, and once our redox potential was sufficiently negative, we followed in an overburdened area. I'll be showing results on our next slide. At first, we'll be looking at chlorinated solvent results, and then we'll go through some geochemical results. So as we get to our next slide, we'll be first looking at some overburden data. If you recall, Montreal 7A was in the plan view slide I indicated was in that source area. And so you can see the timing of our injections. And then these particular slides have our VOCs in micrograms per liter as opposed to moles of ethene. We have the data both ways in both presentations. So anyway, at Montreal 7A, our primary constituent at the outset was dichloroethene. You see after our first injection, it's declining. You can see the rise in TOC, which is that red line. We have increase in vinyl chloride. Our TOC is quickly utilized. You can see we have another amendment and see the TOC rise, and we have some more ethene and ethane at this overburden monitoring well. So if we go to our next slide, we'll start looking at some bedrock results. And our next slide is number 12, and we'll be looking at so if we are waiting, as we wait for the next slide to come up, I'll just say oh, there we go. Okay. I think we might have, there's an interim one we might have missed, but that's all right. Montreal 11B is almost 400 feet down gradient from the bedrock application. And what you can see here is that even at that distance down gradient, we are seeing TOC increase, and we are seeing our daughter products, vinyl chloride and dichloroethene, both decline, and we're seeing good appearance of ethene and ethane at this particular well. One thing I'd like to mention is that we're fairly confident about our bedrock effects down gradient. There was quite a bit of tracer work and also some well fluid replacement tests conducted by one of our colleagues, Jim Schutz, and he presented all these data at IPEC in 2012. IPEC is the International Petroleum Environmental Conference. So if you have any interest in some of the hydraulic applications at this site, you can contact us about that. So now I'd like to go on to the next slide, which will show some geochemical results from a bioremediation program. So the next slide will be number 14. And the upper graph shows redox potential. Bottom graph is on sulfate. Now these are both groups of bedrock wells. And what you can see after the application of our substrate in the bedrock test area, a nice decline in redox potential. As I mentioned, not every well is hydraulically connected, so that would be the case with this uppermost line. In the bottom graph, you can see similarly sulfate reduction in almost all the wells. There are one or two wells up here that are back up in the overburden test area, so they didn't directly have a bedrock application and were not in the flow field of application. If we go to our next slide, on slide 15, we have some more geochemical indicators in our bedrock area. The uppermost graph depicts the total organic carbon results. You can see a rapid arrival of total organic carbon, and then it dissipates, as it's utilized during biodegradation. In the lower graph are our pH results at a number of at a number of bedrock wells, and you can see after the application, which are these solid dashed lines, we have an initial decrease in pH, sometimes getting down to 6, maybe even a little bit below, but then a nice rebound to neutral conditions. You can see most all the results then maintain at about 7, until the timing of the next application, at which point pH declines and once again rebounds. So this is very favorable for biodegradation by dihalococoides. And you can see this happens at quite a number of wells. So in general, very favorable conditions throughout the flow field. So if we go to slide 16, I'll have some microbial results to show you. The microbial results that I'll be showing you are different from these geochemical data graphs in that there are both some bedrock data and some overburden data, that you will see on the next slide 16. And so what are presented here are the dihalococoides population numbers in cells per mil. And as I had mentioned in one of the earlier slides, our initial characterization of the site showed that while it was present, it was low numbers. So we're looking at like 10 to the 1, maybe 10 to the 2. But then you can see right after our first application, which is that green dashed line over to the left side of the graph, numbers immediately begin to rise. We get up to 10 to the 3rd, 10 to the 4th, and continuing, some wells even reach up to 10 to the 5th. So these were very good numbers. We had, well, I can't say that we had almost similar results with Dihalobacter because we really have a lot of data to analyze still from these bioremediation applications. Then when we go to slide 17, I'm just going to wrap up our observations from Site 1. So our next conclusion slide for Site 1 is slide 17. And so I'd like to just refresh what I've shown you today, which is we really had fairly effective bedrock bioremediation at this site. And we believe this is because there were fairly moderate chlorinated solvent concentrations at the outset. We had indicators of natural biodegradation already happening at the site, and so during our bioremediation program, our pH remained neutral. We did not see any hydrogen sulfide. We had a moderate amount of background sulfate, and even better, what happened at this particular site is that these very local applications of our substrate and our microorganisms was able to influence a fairly broad area down gradient of the application area, where we saw positive results even 400 feet down gradient. And so we're very pleased with our bioremediation program at Site 1. And with that, I'd like to turn it over to Glenn, and he can take over on Site 2.
Okay, thank you, Stephanie, and thank you everybody for attending. If you could go ahead and advance the slides, Dora. And as Stephanie indicated, there are similarities and differences between these two sites. And just to refresh memories again, the similarity includes the fact that we're dealing with very similar hydrogeology. The site is located close to Site 1. We will be focusing in this portion of the presentation again on the bedrock. Differences, the primary differences includes the fact that the bioremediation has not progressed to the extent that it has at Site 1. And the question is why? These sites are close to one another. Why the difference between the outcome? And then we'll transition from addressing that question to really using what we've learned in terms of what is limiting biodegradation after an initial injection event and applying that knowledge to optimize a second injection event, and we'll discuss those results. This site has, unlike Site 1, high concentrations of TCE, up to 200 micrograms per liter in the bedrock source area, and DNAPL has been observed. As observed at the first site, this is a naturally anaerobic bedrock system with negative ORP and indications of natural reductive dehalogenation occurring, including native dihalocoquetes and the presence of low concentrations of ethene and ethane prior to the bioremediation injections. This particular site has slightly higher, approximately 4 to 5 times higher sulfate concentration in the groundwater, that concentration being approximately 1,000 milligrams per liter. And we'll be focusing on the influence of that in several of these slides. As observed at the previous site, or Site 1, and Dora, you can go ahead and advance the slides, the pH of the groundwater is neutral. And the next slide will show a schematic, and there it is, of the site. This is a plan view. And Dora, if you could focus on the source area with your cursor there. The bedrock source area is located immediately south of a building located in the northeast section of this figure. And the majority of the data that I'll be describing today came from that area. For frame of reference, extending from north to south in that box is approximately 100 feet. There are several injection and monitoring wells in that area that have allowed for determining differences in how biodegradation has performed on a relatively small scale in that source area. The groundwater flows in general from south to southwest at the site, and you can see the big building in the center of this slide, and then we have monitoring wells to the south of that building or down gradient of the building, and I'll be sharing some information from those wells too. Next slide. And Dora, I'll try to give you a heads up on when to advance the slides.
That would be great. I apologize.
Okay, so in terms of what has been done to enhance bioremediation at Site 2, we will not be focusing on the overburden results. However, I did want to mention that a Bioreactor was installed in the overburden, and this was comprised of a trench backfilled with mulch and vegetable oil. The presentation, or this portion of the presentation, will focus on 2 bedrock injections that occurred in the source area, and that would be the first of which would be represented by the second bullet here. In July of 2011, vegetable oil and bioaugmentation culture was injected into 2 injection wells within the source area in the bedrock, and I'll be sharing information from collected after that injection, and then we modify the next injection event, which occurred in November 2012, to include a carbonate buffer to help neutralize the pH, and we also evaluated the injection of iron for sulfide control into 1 injection well. Okay, next slide. Jumping right into some of the key monitoring data for this site. Here we have the concentration of sulfate over time, and you can see the sulfate decreasing after the first injection event, which occurred at month 0 in this graph. And then the sulfate concentrations typically plateaued, followed by another decrease after approximately 14 months, which is the time associated with the second injection event. At this particular site, due to the higher levels of background sulfate, we did observe hydrogen sulfide accumulation, and we'll be discussing the effects of that on biodegradation. If you could move to the next slide, Dora. I first wanted to give a snapshot of an example well in the bedrock area in terms of the TCE concentrations over time as well as daughter products. There was significant variability in the performance of these wells in this area down gradient or within the bedrock source area, extending approximately 100 feet down gradient. But this well provides a fairly reasonable example. We can see the TCE concentrations decrease, and that was associated with an increase in DCE. And for the most part, that DCE did not biodegrade overly effectively, including in this well. And we did not observe, in contrast to the other site, a net decrease in the total sum of the chloroethene concentrations, and that would be the sum of TCE, DCE, and vinyl chloride within the bioremediation area. If we could go to the next slide. And we'll be showing results down gradient of the bedrock injection. And as observed, as Stephanie mentioned, site 1, we observed nice reductions in CVOCs down gradient. We also observed that at site 2. And if we focus on the data shown in yellow, that curve represents the total molar concentration of TCE, DCE, and vinyl chloride over time for a well that was located 800 feet down gradient of the bedrock injection area, and we can see a nice decreasing trend there. So while we don't see a net decrease in total chlorinated solvent concentrations within the source area, we are seeing net decreases down gradient. Next slide. So to summarize the results of the behavior of the chlorinated solvents, in particular TCE and the degradation products, net reductions in the total molar sum of the chlorinated ethene concentrations was observed down gradient, but we did not observe decreases, net decreases within the source area in bedrock. And overall, after the first injection, the bioremediation performance was not optimal, and we spent a significant effort to determine why this was the case. And at this particular site, we have a significant quantity of monitoring data that allowed us to do that. We noticed that the TCE was fairly persistent in the injection area, including closest to the source, or in particular the upgradient portion of the source area. Additionally, we observed predominantly the production of DCE. So again, a detailed performance was conducted. If you could go ahead and move to the next slide, Dora, to evaluate why biodegradation was not progressing to the extent that we want it to. Again, this is after the first injection. My colleague Jim Schutz and I have worked on this project and reviewing a lot of data together, and we have looked at the data in a number of ways. Jim Schutz's idea was to categorize the wells in the bedrock treatment area in terms of their performance, and then look at the geochemical conditions associated with these varying groups. So for example, we have a suboptimal performance group, which consisted of 7 wells. We had a moderate performing well group consisting of 5 wells, and a good or more optimal situation comprised of 6 wells. And then we compared the pH, sulfide, and TOC concentrations between these wells. And if we go ahead and move to the next slide, did want to make the point that these wells were within a reasonably closely spaced. And before getting into any of the geochemical correlations, I did want to show an example of a more optimal situation where we see TCE concentration decrease, and that was accompanied by an increasing concentration of DCE followed by decreasing DCE, and a suboptimal example where really little biodegradation was observed. And you can see, go ahead and move to the next slide, Dora, where even TCE was not effectively reduced. Okay, this is a figure indicating the location of the performance groups. So that is wells that demonstrated optimal and good performance relative to a moderate cases, and then suboptimal cases in black. And really, you look at this, and well, first, before I get into the information, for reference, from north to south, we're looking at a scale of just over 100 feet. So roughly 100 by 100 foot area, and multiple wells within this area. It's really a shotgun pattern. There's no rhyme or reason, or at least I should say there is a rhyme or reason, but there is no spatial or significant spatial orientation to performance between these wells. However, we've plotted the concentration of sulfide and pH just to the right of these wells, and those values are the average values collected after the initial injection, collected during 6 sampling events, again, after that initial injection. If we focus on the suboptimal wells in black, we see that the pH is typically less than 6.5, and or the sulfide concentrations are elevated, typically above roughly 40 to 50 milligrams per liter. And for those of you that think in millimolar units, we're dealing with over 1 millimolar sulfide in the poor performing wells. In contrast, the wells in blue, where we've observed increased biodegradation, have actually both a higher pH, typically above 6.5, or a low concentration of sulfide. Next slide, Dora. Before getting into the statistical evaluation, of course, we did look at the other indications or parameters that could affect biodegradation. Of course, we have anoxic conditions and reducing ORP. We have ample substrate in terms of TOC, which at this site is primarily, at least what we measure in groundwater, is organic acids, such as acetic acid, propionic acid, and butyric acid, representing the majority of the TOC in groundwater. And that's being generated from the fermentation of the injected vegetable oil. We do measure dissolved hydrogen concentrations in groundwater, and the dissolved hydrogen concentrations are typically above or around 10 nanomolar. We do see concentrations of dissolved hydrogen up to 100 nanomolar. So we have ample hydrogen to fuel reductive dehalogenation. We're also looking at nutritional or potential nutritional limitations. For example, the phosphate concentration in groundwater at the site is often less than 0.0 milligrams per liter. And we have a treatability study looking at that. And then in terms of potential inhibitors, of course, we're going to focus on the next few slides on the pH and hydrogen sulfide. And if you could go ahead and advance the slide, Dora. Try to speed up here because I think we're running out of time. This compares the pH between the good, moderate, and suboptimal performing wells. And here you can see the pH of the good performing wells is roughly 6.7, and that's true both for the mean and median pH, the range being approximately 6.3 to 7.1. And we can see that the moderate performing wells had a pH of approximately 6.5. In comparison, the suboptimal group of wells had a pH median and mean pH of 6.1. If you could go ahead and advance the slides, Dora, please. This plot compares the TOC concentration between these well groups, and you can see that the good and moderate performing wells had a lower TOC relative to the suboptimal group of wells. And the reason for that correlation is that the higher TOC concentrations are correlating with increased concentrations of organic acids that have decreased the pH. Okay, next slide, please, Dora. This is a comparison of the sulfide concentrations in groundwater measured for the good, moderate, and suboptimal groups of wells. And as observed in the previous map, the better performing wells have a sulfide concentration less than approximately 40 milligrams per liter. And in comparison, the moderate and suboptimal groups of wells had sulfide concentrations above 40 milligrams per liter. Okay, you could go ahead and advance the slides, please, Dora. A little more insight is provided here on the hydrogen, the potential for hydrogen sulfide accumulation at Site 2. We're seeing hydrogen sulfide for several reasons. We have a very high groundwater flow velocity in this fractured bedrock, and we have higher background concentrations of sulfate, again at 1,000 milligrams per liter. Both of those parameters yields a high flux of sulfate into the vegetable oil treatment zone, which is stimulating rapid rates of microbial sulfate reduction and hydrogen sulfide generation. If we couple that generation term with some insight on the fractured rock, we know that the fractured rock has low porosity and thus low contact of the fluid or the groundwater moving through that rock with iron-bearing minerals that would precipitate the H2S. So we have a high production term and a low capacity to precipitate hydrogen sulfide in this fractured rock. Yeah, if you could go ahead and advance the slides, please, Dora. This is a plot of the sulfide concentration in groundwater samples relative to the iron concentration on the x-axis. Again, these wells are located in the bedrock treatment area. And as would be expected, what we see is as the iron concentrations, as the iron becomes depleted, the hydrogen sulfide concentrations increase for these samples. And the reason for this behavior is that the sulfide, when generated, if there is iron present, both in groundwater and or on the rock, that hydrogen sulfide will precipitate as iron sulfide minerals. However, over time, that iron can become depleted and eventually the sulfide accumulates. And that's the trend that we see here at the site. Next slide, Dora, please. Okay, so the conclusions to this point. In terms of pH, a pH of approximately 6 is not good. It's definitely not optimal. Depending on who you ask, everybody has a different opinion on what pH is appropriate for chlorinated solvent biodegradation. At this particular site, the data suggests that 6 is not appropriate, and we really need a pH of approximately 6.5 or higher. In terms of the sulfide concentrations, we were able to show that a sulfide concentration of between 20 and roughly 40 milligrams per liter is associated with poor performance. suggesting sulfide inhibition. And given this information, we then modified our injections in November of 2012 to include a carbonate buffer with EVO vegetable oil injections. And we also included injecting iron into one injection well to determine if the iron could be used to control hydrogen sulfide. Yes, and if you could go ahead and advance the slides. Thank you, Dora. The iron injections did include both a soluble source of iron and a mineral source of iron. And the purpose of the mineral source of iron was to provide a longer lasting source of iron for sulfide control. This plot, the upper plot, shows the TOC concentrations over time after the initial injection and then after the second injection again, which included the addition of a carbonate buffer. And for comparison, the pH at the bottom of this chart. And the overall trend here is that as the TOC concentrations increase, the pH decreases, and that's due at least in part and probably primarily due to the production of organic acids, which is decreasing the pH. And then over time, the TOC decreases and the organic acid concentrations decrease, and that's associated with a slight increase in the pH. Overall, we did not see where the addition of the carbonate buffer had a significant or really any meaningful positive influence on the pH. If you focus on the bottom, the pH results at the bottom of the figure, you can see that again, after the second injection, the pH decreased, and really the trends were quite similar as compared to the initial injection where a carbonate buffer was not included. This profile is different than the site that Stephanie indicated. We do have a more significant depression of pH, and that pH is not rebounding as quickly as it did. If you could go ahead and move to the next slide. It's not rebounding as quickly as it did at site 1. The iron injection results were quite interesting. We injected iron, again a soluble and mineral form of iron, into well INJ7D, and that data is shown at the top. The pink line shows the concentration of sulfide in groundwater. You can see the sulfide increased after the initial injection to up to 160 milligrams per liter. We then injected iron into that well as vegetable oil and bioaugmentation culture. And we can see that resulted in a rapid decrease in the sulfide concentration. The sulfide has been maintained at low levels for over 1 year. And we can also see in orange that the iron concentrations in the groundwater increased, as did the production of ethene and ethane, indicating that we've stimulated biodegradation due to most likely the injection of iron. Additionally, we have been able to show or have observed that the injection of iron into one well in the bedrock has resulted in increased iron concentrations in a number of wells down gradient. And an example is shown at the bottom here. Again, we see the sulfide accumulate after that initial injection. We then injected following the second injection event, which included iron. Sulfide concentrations decrease, iron increases, and we stimulate biodegradation based on the accumulation of ethene and ethane. Next slide, please. As indicated, we did see that the iron injections influenced the number of wells down gradient, and in this case, we're plotting the concentration of ethene in units of micromolar over time. And again, after that second injection event, where we decreased the sulfide, we start seeing an increased production of ethene. So sulfide was clearly, if you could go ahead and advance the slides, please. The sulfide was clearly, pretty convincingly was having a negative impact, and the iron appears to be the main reason for the enhanced ethene production after the second injection event. We have collected a significant amount of microbial monitoring data, and overall, what we see at the site and site 1 is that the population of D. halococcoides and the associated reductive dehalogenation genes increases and corresponds with where we see other lines of evidence for biodegradation, such as decreasing TCE and the production or consumption of intermediates. It really makes a lot of sense, or really no surprises in the microbial monitoring data. It corresponds well with other indications of active biodegradation. This is a plot of the bulk microbial monitoring data for all of the samples in the bedrock treatment area, including the Dihalococoides concentrations in green, VCRA gene, which is a vinyl chloride reductase, in yellow, and in white we have the BVCA vinyl chloride reductase. And what we see, and that data is then corresponded or compared with the concentration of ethene in those samples, and we can see there is a positive correlation with increasing cell counts and gene copies relative to the ethene concentration in groundwater samples. Okay, if we could go ahead and advance to the next slide, and I'll go ahead and summarize, and we'll get to questions. Actually, I guess before I do that, if you could go ahead and advance to the next slide, Dora. We'll briefly go through some treatability study results where we're looking at conditions required to enhance biodegradation at the site. We are looking at nutritional limitations, sulfide, and pH. And I'm going to go ahead and, without describing the data in this slide is consistent with the need for both adding iron and controlling pH. When we add iron and adjust the pH to 6.5 to 7, we see TCE concentrations decreasing. If we don't do that, the TCE is not being biodegraded as effectively. Okay, if you could go ahead and advance the next slide, Dora, please. To summarize Site 2, we have learned that as observed at Site 1, we are seeing net decreases in chloroethene concentrations down gradient. I did not mention this during the presentation, but we're also seeing decreases in chloroethene concentrations in the low permeability overburden far down gradient of the bedrock injection area. And we're not sure what the mechanism of that is, but it is becoming more apparent that the injections into the bedrock are having an influence on the CVOC concentrations and the geochemistry in the overburden. And we'll continue to look at that, but nonetheless, it's an interesting scenario where, what we're likely seeing is that by altering conditions and decreasing concentrations in the bedrock, we're seeing an effect in the tight soil overlying the bedrock. Secondly, as indicated, we have a high flux of CVOCs at the site. It really does not appear to be a significant, it certainly is not a roadblock to biodegradation at the site. We're seeing biodegradation. The conditions, however, within the source area, including low pH and hydrogen sulfide, are from what we've seen, key limitations, and we now have information to design our follow-up bioremediation system at this site to account for and address those issues. And that includes injecting iron, and we've learned that injecting soluble iron source coupled with a mineral source of iron was effective at controlling hydrogen sulfide, and that was associated with increasing ethene concentrations. The carbonate addition had little effect on the pH, so we'll be continuing to look at other approaches to improve the pH at this site. And again, the initial laboratory results are consistent with what we've learned from the field. And if you could go ahead and advance 2 additional slides, we'll open it up for questions. But the take-home message, I guess, the take-home message to the bioremediation farmer is that relatively subtle differences between these sites, including the sulfate concentration, has had an effect. And additionally, the for whatever reason, which is not clear, the decreased buffering capacity of the second site is both of those topics are appear to be primarily responsible for the varying performance between these two sites. Okay, Dora, I'm finished. I appreciate everybody's time, and we'll open it up for questions.
All right, thank you very much, Glenn. Thank you, Stephanie. This was a great presentation, and I apologize, everyone, for the delay in the advancement of the slides. I'm not sure what's going on there, but there seemed to be a delay getting it to your computers. So let's go ahead and open up the question session. The first question that we have is, how were the down gradient wells selected for Site 1?
This is Stephanie. So I'm not quite sure what you mean by selected. It means selected that we had for presentation or selected for monitoring. I didn't show all the monitoring data that we have, but there were several wells that were existing, and then others that may have been added based on sort of our estimates of flow velocity, and we did monitor throughout that Site 1 area. Just not everything is presented here because, well, it's just too extensive. I hope that answers your question.
Okay. And then, Glenn, I think you answered this one a little bit later on, but one of the questions is, why was the pH decreasing after the injection? I know you talked about the organic acid production, so maybe if you can just elaborate on that a little bit.
Yes. After we inject vegetable oil, that vegetable oil is essentially biodegraded. In microbiology terms, it would be a fermentation. So they're fermenting the vegetable oil, and the products of that fermentation are organic acids, as well as carbon dioxide. In both the production of organic acids and increasing the CO2 concentrations can result in depression of the pH.
Okay, this question's for you, Stephanie. It says that you indicated that you did tracer testing in the bedrock. What was the groundwater velocity? And then a second part, what do you attribute the low sulfide accumulation to?
Oh, golly, I don't have the groundwater velocity at my fingertips, but I can get that back to you. It was a very high velocity. It's interesting. We have sort of a low gradient and a low porosity, but high velocity, and I can get that exact number to you at a later time. And at Site 1, I believe there are several factors, because we had, when Glenn was talking about that sulfide accumulation potential scenario, because we had several orders of magnitude lower chlorinated VOCs, the amount of vegetable oil that we added at Site 1 is lower because, of course, it's proportional to what you need to degrade. And we had lower sulfate concentrations as background also. So, sort of even though our sites were very similar hydrogeologically, geochemically there was enough subtle variation, like just the difference in the background sulfate, that we didn't see any sulfide generation at Site 1. We were sort of able to stay within the natural boundaries, at Site 1, and really didn't see those depressed pHs continue. And we were able to, sort of within the site domain, maintain that average pH. I hope that answers the question. But there was just enough geochemical difference that really, I think, is what gives us the different performance.
Okay. The next question is, do you know what the concentrations of ferric iron in the soil of the Oberburden for the two sites were?
This is Glenn. I don't think we have that information.
Okay. And then I know that there were different things that were done. Was all of your increase in D. helicoides a result of the bioaugmentation, or did you have some areas that was just an addition of a carbon substrate?
Yeah, we did not independently evaluate the two separately, so we cannot comment on if we were to only add the substrate, if we have observed a similar increase, and it's not clear if the cell population increase is attributed to the injected or the added bioaugmentation culture versus the native Dihalococoides and Dihalobacter that were already present at both of these sites.
Right.
Our approach is in general to go ahead and add a bioaugmentation culture just in case that we don't have the right cells.
Right, and just to elaborate a little bit more on that, we had quite a bit of discussion on whether or not to bioaugment and would we get to where we needed to be for optimal performance. And over the long term, although we don't have the data, I think it's clear that we probably could without bioaugmenting. However, at both sites we had initial pilot tests to sort of prove in the field that this was a worthy full-scale approach, and we only had a short time in which to report our results, and so we wanted to ensure, that over the 3 to 6 months in which we were reporting, we could have the best short-term results possible. So consequently, we bioaugmented.
Okay. For Site 2, the CVOC concentrations appear to be above the solubility range. Do you think there were complications with DNAPL formation in this measurement?
I'm not sure. Could you repeat the question?
Yes, it says the CVOC concentrations at Site 2 appear to be above the solubility range. Do you think there were complications with DNAPL formation?
Oh, I suspect the question might be, did DNAPL get into the sample and cause an increased concentration of TCE with the analytical results? That's not clear. But what is clear is that there are high concentrations of TCE at the site, and DNAPL has been observed.
Okay. And at Site 2, was there geophysical logging of bedrock and or connectivity analysis in the bedrock completed?
Yes, and Jim Schutz headed that work up, and much of that work was presented previously at the IPEC conference, and I would recommend that whomever is interested in that topic let us know, and we'll make sure that you get an appropriate response in perhaps the previous presentation.
Okay. And were you able to conduct groundwater flow and transport modeling to anticipate the effects of the application of SRS, bacteria, and iron?
The transport modeling, to my knowledge, like a mod flow or some other groundwater transport model was not conducted. Really, we use the direct tracer testing to determine flow velocities and to determine where material would where the areas down gradient of the injections that would be influenced from the substrate and bioaugmentation culture injections. So really use tracer tests and again the work that Jim Schutz did to look at the connectivity of the fractures, and also interestingly the connectivity between overburden and bedrock to really understand the flow conditions and the hydrogeology and how that would impact how we implement bioremediation at the site. An example of that is, we've learned that there is connectivity between overburden and bedrock, and in the Site 1 example, we were able to and actually evaluated if injections into the overburden would have a positive effect, including distributing TOC into the bedrock. And as I mentioned during my portion of the presentation, we are also seeing that it is likely that the injections into the bedrock are influencing overburden.
Okay, the next question is, can you share the types of iron compounds that were injected? Was it soluble or mineral forms of the iron?
Yeah, we injected a soluble source of iron. I don't know that the specific formulation of the soluble source of iron would matter too much. You do have to be careful with pH when injecting iron. For example, ferrous sulfate is acidic, So you'd want to use a pH neutral source of soluble iron, or neutralize the pH before it's injected. And then the mineral form of iron, I guess I'm just not going to disclose at this point.
Okay. Do you have plans for how you're going to address the low pH in the future?
We are looking at that. The treatability studies are indicating that bicarbonate, at least in the lab, was effective at controlling the pH. So one of the things that we'll be looking at is using bicarbonate, and that might be, again, this is hypothetical, but it could be a constant injection of bicarbonate within the source area, and allowing that bicarbonate to flow down gradient. So this would be a constant metering of a low concentration, or sorry, a constant metering of a high bicarbonate, sodium bicarbonate solution into an upgradient or into upgraded injection wells. And that approach would be consistent with what we're seeing is to be significant down gradient influence over a large area with materials that we inject up gradient.
Okay. The next question is, based on the experience that you've gained from these locations, what types of site characterization would you recommend prior to injection to help avoid some of the issues, especially with what you encountered in Site 2?
Yeah, that's a great question. In terms of the hydrogen sulfide accumulation potential, obviously you want to look at the sulfate concentration, but also the flux of sulfate. So not just the concentration, but the flux of sulfate. And that's going to dictate the hydrogen sulfide production potential. And then also the ferrous iron concentrations in groundwater. And, if possible, looking at the iron concentrations in soil samples would be useful for determining the sulfide precipitation capacity of the soil. Both of those would be useful measurements. And then in terms of pH, obviously bicarbonate, which can help neutralize the pH, is helpful. But honestly, the whole pH geochemistry, we've looked at this, and geochemists have looked at this for this site, and it's very complex, and I think still very difficult to predict pH. And I know a lot of people are working on that, and there are some papers, but some of those papers would be a good source of some of the geochemistry you can look at for helping to predict the pH.
Okay. The next question is, if iron can't be added to remove the sulfide, do you have other ideas of what options could be available?
Stephanie, chime in if you can think of anything.
I'm thinking of anything else we can use to complex, the sulfide. So I know there are other possibilities. I'm sorry that if they don't come to my, head right at the moment, but to go back to the question earlier, I might also look at the iron mineralogy of the rock if you have a rock situation as we do, because our rock geochemistry, which is now over my head for me to discuss, has a lot to do with sort of our inability to maintain a neutral pH at the site, and our sulfate flux. So there are other ways to complex the sulfide, and if the iron hadn't worked, we'd have done some more exploration with our geochemist partners.
Yeah, certainly iron is is very cost effective. I can't think of a cost effective. You really don't want to oxidize. There are ways to oxidize sulfide back to sulfate. Probably would not want to do that because you're just going to recycle the sulfate. The other thing that we've discussed is reducing the quantity of electron donor that's added. I really don't think in this case that that's going to be overly beneficial. because we're still getting, regardless of how much the concentration or quantity of electron donor or substrate that we inject, we're still going to stimulate microbial sulfate reduction. So, but perhaps dosing the substrate and lower doses of substrate could help. But really, I think in our scenario, we're going to be moving down the iron route.
Okay, great. Next question is, how much do you suspect that the mulch was a source of the organic acids that you're seeing?
Yeah, that's a good question. For these particular wells, not so much. I think there's, it's unlikely that it's clear that the bedrock injections where we directly injected oil into the bedrock was the predominant source of organic acids.
Okay. Do you think that the free product DNAPL in the source area had an impact on the less than optimal performance that you saw there?
Yeah, Stephanie, go ahead. I've been talking a lot. I'll let you take that one.
Oh, well, yes, to some extent, in that because we had high, it all gets to the flux question. We have the high CVOC flux and we have the high sulfate flux, and to address the high CVOCs, there is the need to add the high, a higher amount of substrate, which then leads to the production of organic acids and the pH depression. So maybe not directly, but certainly indirectly, that is the root of our having a lower pH, but not because the pH directly did that.
Or not directly because of the there's no real evidence of like toxicity associated with the high chlorinated solvent concentrations. It's really the sulfide and the pH. So the bugs were happy in the presence of 200 micrograms per liter TCE.
Right, and we had before the outset of the bioremediation program, the DNAPL that was detected and observed was removed. It's not to say that there obviously aren't areas of residual DNAPL at the site, which is certainly evidenced by the high dissolved concentrations. And could there be something somewhere? Yes. However, there was a very large DNAPL removal program before we addressed or moved into a bioremediation program.
Okay. And then with the nutrient addition, can you elaborate on how much you think that the positive impact was from the nutrients?
Well, that's an ongoing treatability study. We do have an initial result indicating that where we added a source of ammonia and phosphate, that we did stimulate the conversion of DCE to vinyl chloride. So that did, that was to this point our best treatment, where we added a source of iron, we increased the pH, and we added a source of ammonia and phosphate. At this point, I would say that it's not clear, the relative value of adding or need to increase the concentration of nitrogen and phosphorus is unclear relative to pH and sulfide control, but we do have an initial indication that the phosphate and ammonia addition may be beneficial, and we'll continue to monitor a treatability study.
Okay, great.
And of course, the goal there is to determine if a nitrogen and phosphorus source needs to be included in the next injections.
All right, and then one last question. For future sites where you are going to be doing a carbon donor injection, do you think you'll collect the same large volume of pre-injection data, or would you just move forward more quickly at this point?
Collect the same volume of pre-injection data. I think the pre-injection data is very valuable.
I do too. I can't see us, really decreasing the scope or the both in terms of parameters or maybe the area, especially for these sites, where we, we're able to determine sort of the down gradient influence of our sort of pilot scale injection. So, I mean, perhaps if the sites were very, very different, but I don't think I would really change the parameter set. I might expand it a little bit just to be sure about how to proceed.
I agree, and I asked that question from one of the members is because we get that question commonly here, and we definitely agree that pre-injection data is so valuable to really understand and know what you're going to be getting when you, add that amendment to the site. It gives you a good base of knowledge for what you're doing moving forward.
Right, right.
So I really appreciate it. You guys did an excellent job. Thank you very much, Stephanie and Glenn. And again, I'm sorry for the delays. Thank you for being patient with us on that. The webinar will be available recorded on our website. If you're interested, we'll send out a link to everyone that attended later this week. We appreciate you being here and joining us, and look forward to you joining us for future webinars. Have a great day. Thank you.
Yeah, well, thank you.
Thanks.